Today I am going to discuss about some problem regarding scalar product. Example. For any two vectors, A vector and B vector, prove that modulus of A vector plus B vector square equals to modulus of A vector square plus modulus of B vector square plus 2A vector dot B vector. Modulus of A vector minus B vector square equals to modulus of A vector square plus modulus of B vector square minus 2A vector dot B vector. And number 3 is modulus of A vector plus B vector square plus modulus of A vector minus B vector square equals to 2 modulus of A vector square plus modulus of B vector square. Therefore, solution. Modulus of A vector plus B vector whole square. We can write this as A vector plus B vector dot A vector plus B vector as modulus of X vector equals to X dot X vector. Now from distributivity of dot product over vector addition, we can write this as A vector plus B vector dot A vector plus A vector plus B vector dot B vector. This is the property of distributivity. Now, if we break this, then we get A vector dot A vector plus B vector dot A vector plus A vector dot B vector plus B vector dot B vector. Now A vector dot A vector is modulus of A vector square and B vector dot B vector is modulus of B vector square and A dot B plus B dot A, this is the commutative property. So B vector dot A vector is equals to A vector dot B vector. This means 2A vector dot B vector. Proved. Similarly, we can prove that modulus of A vector minus B vector square equals to modulus of A vector square plus modulus of B vector square minus 2A vector dot B vector. Adding 2 we get, if we add this, we get A vector plus B vector square plus modulus of A vector minus B vector square equals to 2 modulus of A vector square plus B vector square. These two terms will be cancelled. Now, geometrical interpretation. What is geometrical interpretation? Is OA A, B, C and D. AB vector is A vector, this is B vector, B vector, let ABCD be a parallelogram. A, B, C, D, B are parallelogram. Having sides AB, A vector and BC, B vector. Now in triangle ABC, we get AB plus BC. AB plus BC equals to AC vector. This means A vector plus B vector equals to AC vector. And we get from triangle ABD, AD vector plus DB vector equals to AB vector. DB vector equals to AB vector minus AD vector. Now AB vector is B vector, A vector, and AD vector is B vector. Therefore, DB equals to A vector minus B vector. Thus, A vector plus B vector and A vector minus B vector represent two diagonal of a parallelogram whose adjacent sides are A vector and B vector Therefore, we know that diagonal equals to if A and B be length of two adjacent sides of a parallelogram, then diagonal equals to root over A square plus B square. Therefore, then diagonal square equals to A square plus B square. Now, A vector plus B vector represent one diagonal and A vector minus B vector represent another diagonal. This sum of these two diagonal is A vector plus B vector square, A vector minus B vector square. Sum of square of these two diagonals equals to 2 modulus of A square plus modulus of B square. This implies the sum of the square of sides of a parallelogram equals to the sum of square of diagonals of the parallelogram. This implies the sum of squares of the side of a parallelogram is equals to the sum of square of diagonals of the parallelogram. Number 4, modulus of A vector plus B vector if modulus A and B be two not-zero vector and modulus of A vector plus B vector equals to modulus of A vector minus B vector. This implies that A vector perpendicular to B vector. Number 5, if modulus of A vector plus B vector equals to modulus of A vector plus B vector implies A vector is parallel to B vector. And number 6, modulus of A vector plus B vector square equals to modulus of A vector square plus modulus of B vector square. This implies that A vector and B vector are orthogonal. Now the solution. A vector plus b vector equals to a vector minus b vector. Now, we have to prove that a vector is perpendicular to b vector. So, our target is to prove that a vector dot b vector equals to 0. Means dot product of two vector, when dot product of two vector will be 0? If the angle between these two vectors, that is perpendicular, cos pi by 2, then the dot product of two vector will be 0. So, from this, if we want to derive a dot b equals to 0, we have to square of this, we have to do square both sides. Because if we don't square both sides, then we do not get a dot b. So, in the next step, we square both sides. Now, modulus of a vector plus b vector square is a vector square modulus plus modulus of b vector square plus 2a vector dot b vector. And this is a vector square plus b vector square minus 2a vector dot b vector. From this, these two terms will be cancelled and we get 4a vector dot b vector equals to 0. Now, when a vector dot b vector will be 0, dot product will be 0 when the angle between them will be pi by 2. That means that this implies that a vector is perpendicular to b vector. Now, in previous example, we have seen that modulus of a vector plus b vector and a vector plus b vector and a vector minus b vector represent the diagonals of a parallelogram. Whose two sides are a vector and b vector. Whose two adjacent sides are a vector and b vector. Therefore, modulus of a vector plus b vector equals to modulus of a vector minus b vector. This implies that a vector dot b vector, a vector is perpendicular to b vector. A vector is perpendicular to b vector. This implies. Now, when diagonals of parallelogram are equal, if and only if this implies that diagonals of parallelogram are equal, when these are the diagonals of a rectangle. This implies that if and only if it is a rectangle. This implies, because in rectangle two adjacent sides are perpendicular to each other. So diagonals of, if our diagonals of parallelogram are equal, then those diagonals are the diagonals of a rectangle. Number 5. Modulus of A vector plus B vector equals to modulus of A vector plus modulus of B vector. We have to prove that A vector and B vector are orthogonal. So, when A vector and B vector will be orthogonal, that means orthogonal. No, number 5. This is number 6. Sorry. Number 5, modulus of A vector plus B vector equals to modulus of A vector plus B vector. Implies that A vector is parallel to B vector. When A vector is parallel to B vector means that their dot product is 1. Means A vector, modulus of A vector plus modulus of B vector. Parallel means angle between them is 0 degree. 0 degree. So, our target is, from this equation we derive A dot B, and when we get, it is the only one way to get A dot B is squaring both sides. Squaring both sides. So if we square both sides, then we get A vector square plus modulus of B vector square plus 2 A vector dot B vector equals to modulus of A vector square plus modulus of B vector plus 2 modulus of A vector modulus of B vector. Now these two terms will be cancelled. Now we get that A vector dot B vector equals to 2 modulus of A vector modulus of B vector. Now A vector dot B vector means modulus of A vector modulus of B vector cos theta equals to modulus of A vector modulus of B vector. From this equation we get that cos theta equals to 1. Cos theta will be 1, then theta will be 0 degree. If theta is 0, then this implies that A vector and B vector are parallel to each other. Number 6. We have A vector plus B vector square equals to modulus of A vector square plus modulus of B vector square. We have to prove that A vector and B vector are orthogonal. From this equation we get A vector square plus B vector square plus 2 A vector dot B vector equals to modulus of A vector square plus modulus of B vector square. These two terms will be cancelled. Then we get 2 A vector dot B vector equals to 1. Not 1, 0. 2 A vector dot B vector equals to 0. Therefore, A vector dot B vector equals to 0. This means that cos theta equals to 0. Cos theta will be 0 in only one case, when theta equals to pi by 2. Therefore, the vector A and B are orthogonal to each other. Therefore, this implies that A vector and B vectors are orthogonal. Thank you. Please subscribe my channel and if possible then like.